In this video, we're going to talk about superconductivity. There are some materials for which the resistivity is zero, below a certain temperature. That certain temperature is known as critical temperature. Now, the phenomenon is called superconductivity. It was actually discovered by a Dutch scientist, a physicist called H. Onnes in 1911, shortly after he successfully liquefied helium. Now, these superconductors, we can look at their applications. They are used in the manufacturing of high-field superconducting magnets, which produces no heat. Number two is that they are used in cables for distributing power without energy loss, except energy required to refrigerate the line. Number three is that they are also used in a very sensitive measuring instrument and computer technologies. So let's look at variation of resistivity rule with temperature T. We need to understand that the resistivity of all metallic conductors increases with increasing temperature. So we have that rho T is equal to rho 0, 1 plus alpha into T minus T naught plus beta into T minus T naught all squared. Now, one thing we need to understand here is that alpha and beta are constants, while rho T and rho 0 are resistivity of the material at the metal. The material is actually metals. Resistivity of the metal at temperature T and temperature 0. So we're having two temperatures here, T0 and T. Now, the constant beta is very small compared to the constant alpha. And because of that, for moderate temperature ranges, the law of variation is taken as rho T equal to rho 0 into 1 plus alpha into T minus T naught. We ignore this place because it is irrelevant. Now, we also need to note that the resistivity of semiconductor decreases rapidly with increasing temperature. These characteristics actually is what makes semiconductors suitable for making temperature-sensitive resistors that we call thermistor. So they are used as safeguards against current fluctuations in electrical circuits. So from the above equation, we can make alpha subject of the formula, having that alpha is equal to rho T minus rho naught over rho naught into T minus T naught when alpha is made subject of the formula. You can also have that if you factorize, you can have 1 over that alpha is equal to 1 over rho dp over dt. This is change in resistivity. This is change in temperature. So dp dt, change in temperature, which is this, change in resistivity, which is this 1 over p. That's rule. So because of this, alpha may be defined as the fractional increase in resistivity per degree increase in temperature. So the unit is per Kelvin. The unit is per Kelvin, or you say per degree Celsius. Now, if we have a conductor of fixed length L and a cross-sectional area A, we may use the relation R is equal to rho L over A, if you can remember. And we can rewrite it as R equal to r naught into 1 plus alpha into t minus t naught. So for a given specimen of wire, P, that's rule, and R with temperature may be used to measure the temperature. Okay, moving on. Since the change in resistivity with temperature can be used to calculate the temperature itself. Now let's look at some examples. A silver wire has a length of L equals 10 meters and cross-sectional area A 6 millimeters squared at 20 degrees Celsius. If the conductivity of silver is 5.8 times 10 raised to power 7 ohm per meter, calculate A, the resistivity of the wire, 2, the resistance at 20 degrees Celsius. C, if a potential difference of 20 volts is maintained over the length, calculate the current flowing through the wire. D, find the resistivity of the wire at 100 degrees Celsius. Take the temperature coefficient of resistance alpha equals 3.9 times 10 raised to power minus 3 per degree Celsius. Now, let's look at the first one. We can solve the first one. They said we should calculate the resistivity of the wire. Another definition of the resistivity rule is that it is the reciprocal of conductivity. The reciprocal of conductivity. So, since it is the reciprocal of conductivity, we can say it is equal to 5.8 times 10 raised to power 7 raised to power 1 raised to power minus 1. That's 1 over this. So if we press the calculator for that, we'll have 1.72 times 10 raised to power minus 8 ohm meter. So that will be the resistivity using that relationship. For the second question, they said the resistance at 20 degrees Celsius. We remember that we have a relationship that says that R is equal to rho L over A. Having that, the resistivity already has been calculated, which is 1.72 times 10 raised to power minus 8 ohm meter times the next thing is L. The L given to us is 10 meters times 10 meters over area. The area given to us from the question is 6 millimeters. We will not use it as that millimeter. We'll have to convert to meters, which is 6 times 10 raised to power minus 6 meters squared. So if we press the calculator on that, we're going to have 2.87 times 10 raised to power minus 2 ohm. Okay, the third question says that we should calculate the current flowing through the wire. Now, current flowing is denoted as I. Remember that from Ohm's law, V is equal to IR. If we make I subject of the formula, we can say that I is equal to V over R. So, they already gave us that 20 volts is flowing, potential difference of 20 volts flowing. So, the resistance we've already calculated happens to be 2.87 times 10 raised to power minus 2. I beg your pardon, sorry. Minus 2. So, if you press that in your calculator, you're going to get 696.86 ampere for current. The D says we can calculate the resistivity of the wire at 100 degrees Celsius. Now, the resistivity at 100 degrees Celsius is given as, it started with resistivity of 20, remember, into 1 plus alpha into the temperature is at 100 degrees Celsius minus the initial temperature, which is 20 degrees. So the rho resistivity at 100 is equal to The resistivity at 20, remember we got it to be 1.72, which is 1.72 times 10 raised to power minus 8 into 1 plus alpha is a constant given to us, and they gave it to us to be 3.9. So we say 3.9 times 10 raised to the power minus 8. Yes. So the next thing is the question. Okay, times 10, we have to include, okay, the value is actually minus 3 times 10 raised to power minus 3, sorry, not minus 8, minus 3. So we now have temperature 100 minus temperature 20. So here alone is 80. If we calculate everything, multiply by 80, we're going to have 2.26 times 10 raised to power minus 8 ohm meter.